This video attempts to summarize the concepts and some of the skills in Chapter 9, Regression Wisdom. Mostly it's about the cautions and considerations you should take into account when you are doing regression analysis. And we talked about this idea of checking residuals. Why should we check residuals? Because they're what is left over after the model describes the relationship. And they can often reveal subtleties not noticed in the scatter plot itself. Like you're not really sure how straight the scatter plot is. If you plot the residuals, you might get a better idea, or you should get a better idea. A curve might be revealed that wasn't evident in the original data. And also, sometimes residuals might reveal groups that could or should be examined separately. So you might find these clumps, again, that you didn't necessarily notice in the original data. And I believe we've probably talked about this before, this idea of extrapolation. And that's using the model beyond the original data. And this can be dubious, dangerous, particularly when making predictions far beyond the observed X values. You might consider this idea of 100-meter dash times. If we looked back in history, we might see that these times are decreasing. But can we, look way out to the year I don't know when an Olympic year would be, but let's say, 2050 even. And if this did look linear, could we predict it way out here? Not likely. So extrapolation, you have to be careful about. Cautious. Particularly if you're talking about time, actually. This 100-meter dash in years. I should have put the 100-meter over here. Anyway. You get the idea. The other thing that we sort of revisit, this idea of outliers, but now we're talking about leverage and influence. And outliers are essentially unusual points. They might have a large residual. They might have leverage. A large residual comes when you have an extreme Y value. Leverage comes into play when you have an extreme X value. And if you think about the idea of a lever, the longer the lever, right? Say the easier it is to move something. It might be both. It might have an extreme Y value and an extreme X value. But when is that unusual point influential? Data points are considered influential if removing them changes the regression line. And the interesting thing is that often an influential point does not have a large residual because it's pulled the regression line towards itself. So if it's influential, it's affecting where that regression line goes. So it's going to pull it towards it so that point won't necessarily have a large residual. But if you remove it, then the regression line might change. Let's do a quick example. Here, this is the just checking on page 208. Here's a set of data, and here's an unusual point. What would we say about this unusual point? If we did a regression line, do you think that point would change the regression line? Probably not. Not very influential, and therefore it would have a large residual because the regression line is probably still going to fit this data for the most part. What about this one over here? It's certainly not going to affect the regression line, but it does have a lot of leverage, and we're about to do an investigation that will show that might change the correlation value. And then here's a set of data points, and here's a point way down here. It not only has quite a bit of leverage because it's beyond most of the mean X value, but also has a large residual. What's that going to do? If that point didn't exist, the regression line would probably go through here. That point's going to kind of drag it towards itself. Not really sure because this is so grouped. It might drag it enough that the residual could be small. That's arguable, but either way, you can see the effect that each of those points might have. Also, there's this wandering point. Actually, I ended up calling it the unusual point activity, and you'll see a video for that. And I just ask you to go through it yourself. You don't necessarily have to submit anything for that. That's curiosity. And then what are some other cautions? We have this idea of a lurking variable. It might be a third variable driving both variables. For example, if we find that life expectancy and the number of computers you have in your house have a high correlation, does that mean if I go out and give people computers that their life expectancy will increase? Does the number of computers in your house cause your life expectancy to increase or decrease? No. We can think about that lurking variable. What's that third variable that drives both? Well, yes, it's likely has something to do with your income or your wealth. So just because a relationship is straight and has a high correlation does not mean that one variable causes the other. Correlation does not equal causation. In order to determine causation, you will need a well-designed experiment to determine this, and you'll learn more about that, I believe, at November camp. You guys do that section. And the other caution you should take into account are summary values. If the data is composed of summary values, such as means, it will have less variability than if composed of individuals. So for example, if I went out and randomly selected 50-year-old males across the country and measured their height and weight, what would that look like versus if I took the mean height and weight from each state and made that my data? So summary values are going to have less variability, so they're more likely to have smaller residuals, have a higher correlation value, things like that. So anytime you're doing regression analysis, you also have to really think about where the data comes from, what you're seeing, look for unusual points, check the residuals. Just don't go blindly into it. Okay, so check out the activity about unusual points and then do the exercises, and you have to summarize, submit one exercise.